Good morning. My name is Elizabeth Haitian. Today we are going to present our final project, that is to predict the parking demand in Seattle. We will go through methods, data, exploratory analysis, model building, model validation, and discussion. Seattle, like most big cities, is facing parking shortages. With sufficient total number of parking spaces available, people living in the city still find it demanding to have access to parking spaces whenever it's needed. This might be caused by spatial mismatch of parking needs as compared to the number of parking spaces provided. In this way, studying the actual data of car parking and using the trends to predict future parking demand would be helpful in policymaking. Planners and policymakers can formulate policies for better planning of parking space, adjust the parking fees as a way to leverage the spatial distribution of car parking, release traffic congestion, and assist in other comprehensive traffic analysis. To overview our method, we use the GIS to extract spatial and demographic data and use the R to do multivariate regression for parking prediction. The unit of analysis is the number of car parking in each street segment of a single year. The dependent variable is occupancy rate, which equals to the total vehicle count divided by the number of car parking spaces. Predictors that are independent variables include parking features, street features, zoning, spatial, demographic features, and occupancy in previous 2 years. Then we conducted multivariate regression analysis. The training data is 2018 parking data, and the test data is parking data in 2019. Our data included parking data and spatial and demographic data. Parking data included data in the study area and sub-areas, data obtained time, side of the block, and number of parking space, and also spatial and demographic data. To see the data visualization, total population and population density were calculated based on census tracts. We observed racial distribution patterns. For example, white population clustered on the west coast, while the southeast districts have higher density of people of color. We provided 2 measurements of distance to the city center. City center is defined by 1 neighborhood with the name of Central Business Center and 4 neighborhoods that are categorized as downtown districts. Distance to schools include distance to universities, to public and private schools. We further measured the distance to parks and the field. It's worth mentioning that during the COVID-19, Seattle Open Data published in early April a dataset of operation time and available food delivery regarding cafes and restaurants. By using these datasets, we were able to identify geographical distributions of food access in the city. Last, we want to analyze different land uses and the correlation to parking demand. By creating a 100-feet buffer, we were able to spatial join land uses to each street segment.
So after we cleaned and combined all features together, we did some exploratory analysis before building our model. We first looked at the dependent variable parking occupancy. As we can see here, the graph is approximately a normal distribution curve with values between 0 and 1.3. So we don't need to log transform it. There are few street segments with occupancy over 1 because some cars park on pavement rather than parking slots. Then we divided all variables into continuous variables and categorical variables. Here we plot pairwise relationships between continuous variables. As the relationship correlation matrix shows, there are only few variables that are highly correlated. like pavement condition and street width. We then did several scatter plots of occupancy as a function of several features we were interested in. Only occupancy lag appeared to be the major associations with occupancy in 2018. For categorical variables, we looked at the box plots. Months on the weekday don't seem to affect occupancy much. Among street-related variables, only transit condition affect occupancy visibly. Those streets with principal transit route seem to have lower parking occupancy. Occupancy also seems to vary across different sides of block and different sub-area. These two features could be good predictors. We also looked at the zoning variables. For our model building, we dropped some variables based on our exploratory analysis and tried a few times. Finally, we selected the significant variables to build our final model. The adjusted R-square is only about 0.2. It is pretty low actually, so we might miss some gold features or the parking occupancy just very hard to predict. This is summary of our final model. Then we used the 2019 data to test our model. We plotted the distribution of the predicted occupancy as orange one and the actual occupancy as green one. As the plot shows, the range of the prediction is narrower than actual occupancy, and the mean of prediction seems to be lower. We also did the scatter plots. So as the plot shows, we under-predicted streets with high occupancy and over-predicted streets with low occupancy. We also mapped the model error and tried to find the missing spatial information, but we didn't see any spatial pattern from the map. It seems like it not randomly distributed among the map. That's all we've already done now. We also came up with some ideas to improve our model. We can do some feature engineering like binning some continuous variables and use advanced regression methods like gradient descent. We can also find other features like distance to hospitals and landmarks, or take other parking facilities into consideration, like indoors and parking structures. So that is our presentation. Thank you.